I'm having a crashing with this new upgrade I got from Microsoft. Microsoft just continues to be a nightmare. I hope Satya Nadella is listening to my podcast and feeling ashamed. Okay, so let's look at some evolution aspects of how climate models have evolved. Obviously, each component evolved over time. This is a brief timeline here. So you heard of Suki Manabe, who shared the Nobel Prize for Physics this year in 2021 along with Klaus Hasselmann. Suki Manabe was a pioneer in the early coupled climate modeling. So GFDL, the Geophysical Fluid Dynamics Lab in Princeton, was one of the places that was the hotbed of model development. That's where the original atmosphere and ocean models evolved with Smagorinsky, Manabe, Kirk-Bryan, and a bunch of others. So mid-1970s, mostly atmospheric models were being run with prescribed land and ocean. By mid-90s, there were good land surface models developed along with the atmosphere models, and also oceans with sea ice, with not the same kind of versions of sea ice or vertical coordinate of the ocean model, and so on and so forth. By early 1990s, we had coupling of here just coupling of land, atmosphere, and not at ocean and ice. Then by early 1990s, we had fully coupled models that were global climate models that were being used for climate predictions, early El Nino predictions, monsoon predictions, and so on and so forth. We also started to have independently evolving sulfate cycle models. So we started to get towards chemistry, which was recognized to be very important by then. So land carbon cycle model was evolved. Ocean carbon cycle model was evolved. So at that time, land ocean used to be forced often and run separately just to explore carbon cycle processes and so on. Atmospheric chemistry also evolved at the same time, and you can see that atmospheric chemistry remained uncoupled for some time. And by the late 1990s, remember the discussion on global warming kicked into high gear in the early 1990s. By late 1990s, we already had one or two special reports from the Intergovernmental Panel on Climate Change. So earlier models were already running with atmosphere, land, ocean, sea ice coupling, as well as sulfate aerosols, which had mostly what are called direct effects, so that they were just affecting radiation without necessarily affecting cloud processes, cloud microphysics, and so on. And then land carbon and ocean carbon models were coupled by the late 1990s to create carbon cycle models that were run offline, in the sense they were not interacting with the climate, atmosphere, ocean. They were just using the atmosphere, ocean circulation to just do carbon cycle. Non-sulfate aerosols also evolved in the late 1990s. Aerosol science became more and more common by then, because we were understanding more and more about aerosols, their direct impacts in terms of radiation absorption, scattering, indirect effects in terms of their impact on just not just clouds and precipitation, but even other things like hurricanes, monsoon circulation, and so on and so forth. Then dynamic vegetation models evolved, which means the vegetations were not just fixed in space and time. They began to respond to seasonality, to various levels of functional types, C3, C4, tropical forest, boreal forest, temperate forest, and so on. And various feedbacks began to happen also. So atmospheric chemistry still remained uncoupled and running a climate model with atmospheric chemistry turns out to be very, very expensive, because you're carrying many species, and each time step you have to do all the reactions, advect them, diffuse them, mix them, and so on and so forth. But present day, let's say this was already an old figure. We have atmosphere, land surface, ocean, sea ice, sulfate aerosols, non-sulfate aerosols, and carbon cycles coupled. So AR5 already had many models that were called Earth system models as opposed to climate models, because they were doing carbon cycle, and many of them also had carbon cycle feedback. But you can see that not many of them had land ice. So land ice was represented. Sea ice was there, but glacier dynamics ice sheets were not there. Even now, not many models have explicit ice sheet modeling and their impact on ice albedo feedback and so on. They're represented using satellites. The albedo and their energy exchange and so on are represented, but they are not dynamically evolving and responding at the time scales that we are looking at, from industrial revolution to 2100 and so on and so forth. So early 2000s we are so this is guessing at that point, but we do have now many models like GFDL latest version running along with all these components. It's also running with dynamic vegetation, and each model gives you an option of turning on and off various things. So even though everything is present, you can turn off some aerosols, you can turn off the carbon cycle, you can turn on and off the dynamic vegetation, you can make them respond and not respond to climate, global warming, and so on. And atmospheric chemistry is already also part of many models and integrations. Okay, so another way to look at it is this, where we are going from 1960s to 2010s again. Atmospheric land surface vegetation models, ocean model, coupled climate model, and sea ice model happened in the 1980s. Sulfate aerosols, dust, sea spray, carbon aerosols, interactive vegetation, biogeochemical cycles, carbon cycle by the 2000s, and by the 2010s, so this is much more updated figure, we have many models with ice sheets, as I mentioned, marine ecosystems, nutrients, zooplankton, phytoplankton, carbon cycle, radiation penetration in the ocean, active participation of the marine ecosystems in the carbon cycle, export of carbon as organic carbon to the bottom of the ocean, atmospheric chemistry, upper atmosphere. So it's become more and more clear that the stratosphere troposphere interactions and representation of the stratosphere, better representation or with higher vertical resolution are also now important for many processes of energy and climate variability. And models always need to be evaluated. It's amazing that given the energy at the top of the atmosphere, these models are able to produce trade winds, westerlies, ocean circulation, thermohaline circulation, monsoons, El Niños, and so on and so forth, and yet they are not quite perfect. So evaluations are done constantly. Here is a multi-model mean surface temperature. You can see the patterns we have seen before with warm temperatures here, the colder to warm contrast. You can see this is warm temperature over 30 degrees, the Himalayas, high latitudes, Greenland, Antarctica. But when you look at the bias or difference between model rendition of the temperatures versus observed estimates of temperatures, you can see there are large differences. There are differences of over 5 degrees colder here. There are differences of 5 degrees warmer here. Now if you use your knowledge of ocean circulation, you know that this was the Benguela current, this was the Peru current, this was the California current, and so on. And you know that this is cold because of upwelling, and if the model is really warm, that means the model is not doing enough upwelling. The same thing here. And it's cold here. We know that mean temperatures here are cold. the models are colder than observations, which means they have somehow produced either too much upwelling or some other process by which sea surface temperatures are colder than what nature produces, and so on over land as well. Okay. Temperature is an easier dynamic variable to simulate. Precipitation turns out to be much more problematic. Why? Because precipitation is like popcorn. There are moist processes involved, instabilities involved, nonlinear convection involved, parameterization of cloud processes, and rainfall and convection are involved, and there are multiple parameterization schemes available because many groups develop these parameterizations based on specific data. So a parameterization of convection that works very well on land will be different than the one that works very well on the ocean. For a large continent like the US, there are processes that are very different in the middle of the continent versus a place like Florida, which is much more tropical. Elevated convection versus ground level convection, all sorts of details exist. So temperature can be the same over a large region. It's called the decorrelation scale, but precipitation will be very small scale. In the same town you are in, it may be raining in one place but not in the other place. So precipitation in general is a very difficult process. So here is the multi-model mean precipitation, which shows us the ITCZ, the monsoon, the SPCZ, and the storm tracks, and so on and so forth. And yet there are biases. If you look at the multi-model mean bias, that means you average many models and you take the difference with observations, and you can see that there is less rain in the ITCZ here, less rain in the ITCZ here. There is too much rain in this region which shouldn't be raining so much. There is too much rain here, there's too much rain here, too much rain here, and so on and so forth. So there are some biases that are known for a long time, and they have persisted for a long time. Large groups, lots of groups work on trying to improve these model biases, but often either we don't know the processes, or we know them but we just don't have enough data to represent them better, or enough theoretical understanding to represent them better, and so on and so forth. So it's like sausage making. Modeling is very difficult. Improving resolutions from, let's say, 100 kilometers to 10 kilometer improves many things, like orographic rain. If mountains are represented better, you expect the orographic rain to be represented better. But there are some processes which don't necessarily get better just by improving resolution, because the basic process may be missing. Something, let's say, like the Gulf Stream, it separates off the coast around Cape Hatteras, but just improving the resolution doesn't necessarily improve the representation of the Gulf Stream in the models. I'm just using that as an example, but there are many such examples. So process understanding is needed, and then representation needs to be improved in addition to providing more resolution. Also, it turns out many times you may need certain feedbacks that are missing in models. For example, in the East Pacific, where I showed that the model sea surface temperatures are too cold, that's also the region of upwelling with a lot of phytoplankton. So the interaction of the phytoplankton with radiation coming in turns out to be very important, and that interaction between energy balance and chlorophyll is not always properly represented in models. So just improving resolution doesn't necessarily improve this missing representation, and so on. So there are many such examples, but you get the idea. Okay.